Now, projectile motion is motion in two dimensions. And you can see, for example, with a ball that has been tossed off of a building, it not only has motion in the x direction, but it also has motion in the y direction. And in the y direction, it's affected by the Earth's gravity, so it is accelerating. And in the x direction, in the absence of friction and air resistance and everything like that, there is no force in which to accelerate our position, in the x direction only. Now we can take our projectile and we can write its velocity in terms of components. Now if you consider a projectile that was flicked off of the edge of a table, say, then initially it has some velocity in the x direction, and its velocity in the y direction is equal to 0. It's not moving downward. Now we can write our acceleration, which is due to gravity, that only acts in the y direction. It doesn't act in the x direction. So we can split up our two components, the x direction and the y direction, and we can consider this two-dimensional problem as two one-dimensional problems, one in the x and one in the y. Now let's start with the x direction first, because it's simpler. Our velocity in the x direction simply does not change as the projectile moves from the right to the left as well as down. It's a constant. There's nothing to accelerate it in that direction. Now, in the y direction, we've already dealt with falling balls. We know that the ball is going to accelerate due to gravity, and its velocity vector is going to change, and it's going to become longer and longer and longer as it falls further and further, thinking strictly about vertical motion. And we can superimpose that velocity vector in the y direction on our ball, and we can write the total velocity as the sum of the x and the y direction. And again, the x doesn't change. The y accelerates downward due to gravity. The velocity changes. So our total velocity becomes larger and larger. Now, this image right here simply shows a graphic of what we talked about on the last slide, where we flick a ball off of the table. That's the yellow ball, and it initially has some x velocity, and it initially has no y velocity, and the red ball was simply dropped at the same exact time. It had no x velocity and it had no y velocity. Now we know that it's going to accelerate downwards, changing velocity as a function of time, and the position increasing quadratically as a function of time. And if you look at these two balls, they fall very nearly side by side. The only difference between them is the yellow ball has some horizontal component to the velocity, and the red ball does not. Both of them fall, however, at the same rate. Now, we can look at projectile motion of a ball that has been thrown in much the same fashion, where we're going to split it up into the two dimensions. So suppose I have a ball that has been thrown, and I know that it's been thrown up at some initial velocity and at some angle. The first thing that I want to do is I want to break this up into its x and y components, where I say the initial x velocity is equal to, let's see, that is the adjacent, so it's going to be the initial velocity times the cosine of the angle, and this one right here is going to be the initial velocity times the sine of the angle. And I treat this in the same exact fashion now as a ball that was dropped. I have some acceleration downwards that is due to gravity. If I look at my initial y velocity arrow here, the acceleration is in the opposite direction. So the acceleration is in the opposite direction of velocity, so it becomes smaller. At the very, very, very tippy top of the arc, the y velocity is 0. It's not moving up and it's not moving down. This is a very important concept to keep in mind. And then the ball starts to accelerate downward, just like a falling ball that we've treated before. Now, in the x direction, there is nothing to accelerate the ball in the x direction, so much like on the last slide, the x component of the velocity is unchanged. And again, we can write our total velocity as the sum of the x and y components. So in order to solve projectile motion problems, again, we split this up into two components. We split it up into the x component and we split it up into the y component. And here we're going to say, you know what, we're going to define the positive y direction to be up and the positive x direction to be to the right. And we know that there is always an acceleration downward. This acceleration is due to gravity, and it's 9.8 meters per second squared. So when we look at the vertical motion, we have to keep in mind that the acceleration is actually going to be in the negative direction. So thinking back to all the equations for one-dimensional kinematics, here we've simply replaced the x's with the y's, because we are talking about the y direction, we don't want to get confused. And rather than have plus acceleration times time, we've written minus g times time, because the acceleration is equal to negative 9.8 meters per second squared. Now in the x direction, we don't have any acceleration, so here we've taken out all of we've set the acceleration equal to 0 and written the equations of one-dimensional kinematics that we're already familiar with. So in order to solve projectile motion problems, same as what I'm always going to tell you, read the problem, read it twice, and choose what you're going to analyze. And then what you're going to do is you're going to draw a diagram. We have a ball being launched at some angle. Choosing the origin and coordinate system, usually you choose where the ball was launched from, and the coordinate system x, y, up, down. And then all we do is, much like I talked about on the last slide, we can write our x velocity, we can write our y velocity, and we can solve these components separately, where we know in the horizontal there is no acceleration, and in the vertical there is acceleration due to gravity. Also, keep in mind for projectile motion that the ball is going to go up, and at the very, 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 very tippy top there is no y velocity. That will allow you to solve problems to where maybe I'll say you throw a ball upwards from rest. How long did it take before the velocity was equal to 0? And then we simply use the equations that we talked about 2 slides ago to proceed. Sometimes you're going to need to use more than one of them depending on what you've been asked to solve for. Now, the last thing I want to talk about is relative velocity. We considered relative speed at one point when I talked about the people on the train. In 2 dimensions, it's really kind of the same thing. We're adding the vectors in 2 different directions, and we're already pretty familiar with that at this point. So, for example, if I consider myself being in a boat and I want to reach the opposite shore, then I start to crank the motor up on the boat and cross the shore. However, there is some river current that is going from the right to the left, so I have a velocity of the boat with respect to the water, and I have some velocity of the water with respect to the shore. So if you are sitting here on the shore, and you say, what is the relative velocity of the boat with respect to the shore, then I can simply write that as the sum of the velocity of the boat with respect to the water and the velocity of the water with respect to the shore. And looking at my simple diagram, you would see I'm going to not go straight across the river as I might like with respect to the shore. I am going to go a little bit in the direction of the river current. So this is our summary, and I'm just going to pause here for a second and let you jot some notes down.